So welcome to week 8. Today we are dealing with the very extreme objects, a neutron star as well as a black hole or black holes. So basically after the end of the death of the stars, or massive stars, they leave behind these corpses. Okay. So let me, do I already share screen? Yes. So enter slideshow. So as I said today, the most extreme objects, the neutron star, pulsar, magnetars, which are basically particular neutron stars, and the black hole. So we have seen the life cycle of a star is massively determined by the size, by its size. If you have a small star, what means everything below, certainly below 3 solar masses, might end up as a red giant, becomes this planetary nebula. By the way, now I know why this one is called Eskimo Nebula. So basically that's the face, and that's the anorak, so the head of the jacket. I know. And well, the remnant will be this white dwarf. So the core of maybe carbon, oxygen, if at all, so neon, that's it. Which will bloom away, become a black dwarf, that's it. By the way, from all these dwarfs, we had no red dwarfs, which were the smaller stars than our sun. White dwarfs, black dwarfs, I think I've forgotten to mention brown dwarfs, the fourth type of dwarf. I know we have more than in the average fantasy book. Brown dwarfs are basically stars that are just at the limit, I think 6 to 8% of the solar mass, that the pressure is enough that they occasionally, when it becomes dense, they start a nuclear reaction. So they produce energy. What of course makes them, heats up the core expands a bit. So temperature goes up, pressure goes up. The density becomes too low. What means now, again, the pressure drops, the temperature drops when it expands. This Maxwell-Boltzmann distribution shifts towards the low energy side, and there are no reactions going on anymore. Then everything cools down, the core contracts again, the critical density is reached, it starts producing a bit of energy, but not too much, and an internal cycle, but no sustaining nuclear reactions. So this heat somehow comes to the surface, and they are relatively low in temperature. And it will be very interesting to see how many of them are there. Maybe James Webb can give us their feeling how many brown dwarfs are out. Of course, hard to see because they are relatively low temperature below. That means the Planck spectrum is just on the edge, maybe the high energy tail comes into the visible, the rest is infrared. How to see them. Okay, that was an excursion to the brown dwarfs. So now we should have done the collection of astronomical dwarfs. Then we have seen if we are above 3 solar masses, or certainly 8 solar masses, the behavior will be completely different. So this is again theory, what enters there. What is in the model included and what is neglected. Or as Vitek Nazarevich, one of the gods of nuclear structure physics, likes to say, theoretical nuclear structure physics, every model is wrong. It's just a question to which degree is it wrong. Some of them are almost correct. So a model will never really reproduce the complexity of nature. Nevertheless, often they work for at least for part relatively good. For example, the atom, we are so good in describing it, it's amazing. So, okay, so it's either 3 solar masses, but certainly 8 solar masses are enough that we will go rather to a red supergiant. So something like Betelgeuse is, well, which then certainly will end up as a supernova type 2. So, and the remnant is now depending on the mass of the star. Some give 15, some give 25, some give 30 solar masses as upper limit. When a neutron star will result from this nova. So here, artist impression, of course, or whether there will be a black hole. Above, there will be 30 solar masses, there will be certainly what is called a black hole. But this will be today's aim, to go for them. So here in the Crab Nebula, which we had now quite often, this supernova from 1054, somewhere in there we find the neutron star remnant. In fact, by now we know about 2000 neutrons, more than 2000 neutron stars just in the Milky Way. Quite some number. But what comes now is relatively theory based. Yes. Most of the stuff is theory based. For example, the structure of a neutron star. We would now assume it's pure big block or big sphere consisting purely of neutrons. Where do these neutrons come from? You remember at the end, when the iron core exceeds this time of Chandrasekhar mass, that it's energetically favorable for the energy to combine with the protons and form neutrons. And all this, or many of these iron nuclei that we are breeding with time, fall apart and just form neutrons. Many of these neutrons fly away, but obviously also a good amount is then later trapped. And the driver is this gravity. It's really the massive gravity that is then present in this core. Oh. So basically that's then the corpse of this massive star. Let's say it's between 8 and 29 solar masses. So roughly. Okay, then it's quite interesting. We have the envelope, so atmosphere, which is still often normal nuclear matter. This bit of an envelope, crust, and then the crust goes over to the inner core. The effects going on with superfluid neutrons, and we still have occasionally phases of normal nuclear matter. About 5% of a neutron star are still protons. And then when we have a higher proton density, we would talk about more or less normal nuclear matter, but this is not exactly true because we're going to see later a neutron star has at least twice the density of the atomic nuclei that we find in our bodies. So, and then we get this bubble phase, and then comes basically some kind of what we call a pasta phase between the neutrons in this superfluid state. Superfluid state means in order to get superconducting, you remember neutrons have this spinor half. Spinor half particles are these fermions which are loners. In order for superfluidity, we need to pack a lot of particles in the same state that they see each other, but avoid each other somehow. No, they don't. they don't really interact. They can nicely wobble around without any kind of resistance. And in order to do this, two neutrons need to pair together and form what is called some kind of Cooper pair. And in superconducting, it would be two electrons. And then we have 2 times half integer. This makes an integer number. 2 times a half is 1. Or if we underline it, 0. Here we talk about then a boson, a quasi-particle boson, or very strange terminology, don't worry about. And this stuff becomes in superconducting. It means they can fly through each other and don't really interact. No resistance between them. Very likely we must have the mix between 0 and 1, where they anti-align and couple and also 1, because there's an observation letter. Well, and then at some point, when the gravitational pressure becomes larger than this pairing force, there must be a decoupling. And this pairing force is very strong in nuclei. And in between is then this what is called the pastar phase, or long stripes where we have matter of one or either type. And then comes another bubble phase where we have the more or still some phase or areas or volumes left with superconducting, and then we go to the core where this is broken. And at some point the pressure is so high we don't know whether we there still have neutrons, or you remember the neutrons consisted of these quarks, 3 quarks, up, down, down. And they were somehow glued together by these gluons, and when you make the density so high, usually they repel at each other, the 2 neutrons, but maybe you break this what is called confinement, and what you get is a big soup consisting of these quarks and these gluons. That is called a quark-gluon plasma. Well, when I was a PhD student, there were even claimed that people have observed something from the mass to volume ratio. It would have been already the entire star would have been just a quark star. Although we wouldn't have talked anymore about protons, it would have been rather, if you take a proton to be an egg, then you smash them all in a bucket, and what you get is the soup. Don't talk anymore about eggs, you talk about this scrambled egg maybe. So, but here this is all very, very theory based. Well, so how does this matter really behave? The crap is, we don't really know. We don't really know how to describe nuclear matter at twice the what is called saturation density. Saturation density would be the standard in nuclear physics. So the one that you have seen, this semi-empirical mass formula, or the Bethe-Weizsäcker plot with the binding energy that a mass unit that then starts to saturate, that would be at saturation density. So for me they are very interesting because they are basically the largest atomic nuclei. And so I should have around 2 solar masses. So what means for me, these are the only nuclei where gravity plays a role. Usually gravity is so weak compared to the other force we can neglect it. But here we have so much matter in a small volume assembled that this plays suddenly a role. So basically, if we plot them in this table of isotopes, that would be going here towards the right-hand side, which is towards, for me, east, means since today, unfortunately, next to the Russian tanks. So very far on this side, 2 times the solar mass. You can calculate now how many neutrons are. in comparison to this standard neutron mass. So the heaviest atomic nuclei, and for them gravity really plays a big role. Otherwise, because the neutron excess is now so high, there would be immediately radioactive beta decay to standard nuclear matter, and the stuff would start to dissolve because the Coulomb interaction would become too strong. So and the gravitational energy that is there involved corresponds to, if we would take the mass equivalent, it would come down to roughly a solar mass. We're just in gravity. Or if we take our sun and make it pure into energy, give you a feeling, I think Hiroshima was about 100 milligrams. But this is something I would have now to look up, how much mass Hiroshima was. So then you take our sun and turn it into energy. So otherwise, these neutrons would immediately decay to become to equal number of protons. By the way, I see here the neutrino mass that I give here is very old limit. Obviously, I haven't updated the slide since the last 3 years. The last value I have heard now was 0.8 eVolt. So just a third of that what is given here as upper limit. Oh. And now it's of course interesting how big are these objects. Well, if you remember white dwarfs, so a white dwarf, I didn't really mention this, but about 70% of solar mass or 50% of the solar mass, and about as big as the Earth. So, wow. That's, if we compare this, a neutron star, about 2 times the mass of our sun. And the radii must be about between 12 to 14 kilometers. This is what is observed. So a radius 12 to 14 kilometers, and you press twice the mass of our sun. Then you end up with twice the density of normal nuclear matter. Okay, so something very impressive, but about 12 to 14 kilometers. If you make a diameter, 24 to 28 kilometers, 20 miles, or we are about the size of Manhattan. This is then here 1.5 to 2 solar masses. Oh, quite tough. Okay, now we can look 12 to 14 kilometer radius. These are experimentally observed solar masses of neutron star. So you see 1.4 to about 2 solar masses. And what you see here coming in these lines, this is basically nuclear models trying to describe these properties. And they should end up somewhere here. And effectively, these two maybe do it. The other ones give us too much masses for the ones. Some give us too short or too small of a radii, so too high of a density. Only these two models are doing reasonably well. By the way, this plot has been made by Vitek Nazarevich and Jacek Dobachevsky, so 2 geniuses. And what do we see? Our models that describe nuclear physics in the lab quite well. doesn't work for nuclear physics in neutron stars. But that is to expect, because this density dependence, this is really a problem at the moment. How to describe it? And in fact, now neutron stars becomes labs for us. So astronomical observation become now labs for me as nuclear physicist to learn about nuclear matter. Sorry, I need quickly on my nose. Oh, sorry, small cold. So hopefully this gives you a bit of a feeling what is going on, and now it becomes interesting. In order to escape from a body, we need a certain velocity of the body that tries to escape from this gravitational field. I could quickly model this for you. On the other hand, it's going to be, this is a very relatively interesting lesson, so you probably gotta listen to anyway. So I'm gonna stay tuned in anyway. So let's quickly plot this, what is going on here. No, that's the software, that's the pen. So hopefully you see now the tablet. Okay. What we make is now again one of these potential energy surfaces. Okay, this is again. Why does this always happen? Made in China. Okay. Now we should be able to nicely plot this. So potential energy curve. So here's the energy. Zero, but zero means above the particle is unbound. The body is free to move wherever it wants. Otherwise, it's somehow trapped if it's below. And then we plot here the distance or the radius r. So how far from the center is this away? And then we would have this 1 over r behavior. This is typical of. So the potential energy V of r is proportional to 1 over r. If we make here the derivative, that would be proportional to minus 1 over r squared. So the typical Newton's gravity law. So with this hyperbola, that must be minus to have it negative. Okay, now we have a certain surface of our body, the radius. That is r. Since we have spherical symmetry, we can nicely say this is all coming from this point in the center and then goes away here. This is r. What means we start now here and want our rocket to go out into space. Somewhere here. And in order to be free to move away, we obviously need to overcome this energy difference, delta E, at this point to 0. Or the kinetic energy that we put in the system here to come to here, to somewhere here. So this point that would be in this diagram somewhere here, but 0 potential. That must be the kinetic energy. So, oops, mv squared over r. Mv squared half, sorry. So now we can basically delta E over m 2 times square root of it. This is our escape velocity. We could now also calculate this delta E in terms of potential energy. That is from R to infinity, V of R, VR. And the work would be force. The force is that is the force. Then multiplied with R, that we are the energy. Force along the way, and then we get the work that we need to invest, and this we can then plug in here for delta E, and we get directly for the velocity. And this is the minimum velocity we need. This is the so-called escape velocity. Now what we see, the smaller the object, the deeper we are trapped here in this potential well. The more must this delta E here to be. The higher must be this escape velocity. So basically here in a well, and in order to jump out, well, there's a certain depth where you need to be so fast to make it, and or that your rocket needs to have a certain thrust. Okay, so this would be explanation of escape velocity. Upsilon. Hopefully I still have this all shared. Oh, from current slide. Oh, no, sorry. From current slide. So now it turns out for the surface of a neutron star with roughly 2 solar masses and 13-14 kilometer towards the center, we are quite deep in the well. That means the gravitation on the surface of the neutron star is 2 times 10 to the power of 11 times stronger than on Earth. That means if you place yourself on the scale and you're just like me, 100 kilograms, you have now 2 times 10 to the 13 kilograms. A ton is 10 to the 3, so 10 trillion tons. No, billion tons, sorry. 10 billion tons. Need a good scale. Okay, and in terms of escape velocities, if we calculate this, this is 100 to 150,000 kilometers per second, not per hour, per second. Which means a third to half the speed of light. Or one would be very flat on the surface of a neutron star. Or the physical height would be basically 0. Very impressive stuff. Interestingly, theory was here again well before experiment. Interestingly, Lev Landau, the great Lev Landau, he proposed neutron cores in stars already in 1931. 1933, Walter Bade and Fritz Zwicky, 2 Swiss lads, proposed neutron stars, that they should exist. Interestingly, the experiment, 1935, so 2 years after Bade, 4 years after Landau, Chadwick has proven the existence of the neutron. Before we knew it, there must be something that is neutral and it's about the same weight as the proton. But it wasn't direct or not really observed. This was done by James Chadwick. I think it was in Manchester, so UK. Well, 1967, Dame Jocelyn Bell Burnell, Anthony Hewish and Martin Ryle discovered radio signals of a pulsar, which then was identified as rotating neutron star. Nowadays, more than 2,000 of them are known. And 2017, August, for me, and many of my colleagues, very exciting, the merging of two neutron stars. To give you a feeling about these people and give you a smile, the great Lev Landau, I wonder how he slept, because I wonder how you can make such a hairstyle. If you buy the book on your head or whatever. Yet one shouldn't judge the content of the head by the hairstyle. Landau and his friend Lifshitz, they have written some books together about classical mechanics, thermodynamics. By the way, Landau, if we talk about phase transition, so between water and gases or liquid and ice, we still use the formalisms developed by Lev Landau. So, and these books, they are still classics. Classical mechanics, thermodynamics, Landau, Lifshitz books from electrodynamics. There's an old story that at some point Lifshitz came to Landau and was completely almost in tears, and then saying to Landau, "Oh my God, I worked for 2 months for 2 weeks at a proof to prove something. But now when I came here, I wanted to have a check, so in the tram I had it out, and now I forgot it in the tram." And then Landau just says, "Yeah, so exaggerated. Just do it as we usually do and write down as it's easy to see, as it's trivial." So the books are quite often this way, and usually for most of us, these things are not trivial. But so a great mind, Lev Landau. Well, here you see this lighter body, and then Fritz Zwicky. Fritz Zwicky seemingly quite liked some good argument. So, well, here you see him a bit more friendly. And then to give you a feeling of Dame Jocelyn Bell Burnell, in front of the Mallard Radio Astronomy Observatory, somewhere in Cambridgeshire, run by the University of Cambridge, where she was doing her PhD. Well, I do not show now these two guys because they got enough. They got the Nobel Prize for her discovery, and she got nothing. But this is my little protest against this decision by the Nobel Prize Committee and these guys, because this is disgusting, and at some point you've got to say, as much as you want the Nobel Prize, then you have to say either she too or not. And what did she discover? Well, here's the original notes, and you see basically occasionally here something, and here this occasional or very regular basically signals. So what turned out that the pulsar B 1990 plus 21 in a distance of 2000 light years, and it has a period length for this repetition of 1.337 seconds. And the change of period length, if one measures it now with atomic locks, it comes down to this 1.348 10 to the minus 15 seconds. Otherwise, this stuff is really almost a metronome, like when you want to do music and you have this instrument that gives you the tempo. And it emits radio waves from 85 megahertz to 2.7 gigahertz, so in the wide range. but very periodically. So the period length is here shown again between, and then we always for a short time. And if you got something really periodically, you think that's a lighthouse. I tell you, the next thing is nature really that repetitive? Or the first thing is, of course, you think it's one of these guys. Oh. But it can also be a rotating object that ejects radiation into space. And every time that is somehow going on a circle, and you are at some point of this circle, and every time it hits you, you get the signal. And people then quickly realize that must be a rotating neutron star pulsar. So now I would recommend you tune in to this video that is given here in the link, and enjoy basically how the neutron star rotates, but the pole, the magnetic pole, is not aligned with the rotation axis. And along this magnetic pole, the axis, magnetic axis, there comes now this radiation, is ejected into space. And why? We're gonna clarify it following this video. So watch this video, take a bit of a break, get your head clear, walk a few steps, and then tune in for the next video. See you then.